Yes, I welcome you to this video lesson, which will focus on hypothesis testing when the sample size is large. Like we said in the previous video lesson, samples are classified as being large and small based on the size. When the size is at least 30, we classify them as large. And today we'll look at how to solve problems with hypothesis testing for large samples. Before we get into specific problems, we'll identify the methods based on which the critical value and the critical region are identified for large samples. This is done based on two aspects. Number one, the type of test that is being performed, and number two, the level of significance. So whenever the sample size is greater than 30, we can approximate this using the normal distribution, and therefore all diagrams that will follow will resemble the area or will resemble the normal distribution curve. For the first example, I've considered a two-tailed test at 0.05 level of significance, which means the critical region is along both extremes of the sample space, one on the left and one on the right. And since the level of significance is at 0.05, we consider splitting the 0.05 into two equal halves, one along the left extreme and one along the right extreme. So adding up the two areas at 0.025, we see that the total area is at 0.05, which is the level of significance that we have considered. So the critical regions are towards the extremes, and the confidence interval is along the middle, and then we have a critical value which follow the border. So to find the critical value, we use the normal distribution chart. We consider one particular extreme, and that is enough because of the symmetrical nature of the normal distribution curve. So we have seen that the area of the critical region, the right extreme, is at 0.025. So this is the area to the right of the critical value. Therefore, the area between the origin and the critical value will be defined by 0.5 minus 0.025. The 0.5 is obvious because the entire distribution is symmetrical. The total area is 1. So left half is 1 and the right half is 1. So the right half entirety will give you a 0.5. And from this, we subtract area to the right. So we are looking for a critical value which has an area or which has a probability that it lies between 0 and the particular critical value at 0.475. Now, using the normal distribution, we are able to identify that this critical value is at 1.96. So this is 1.96 and its extreme opposite. The minus 1.96 will denote the two critical values for the two-tailed test that we are considering. So for a two-tailed test, at 0.05 level of significance, the critical values are at 1.96 and minus 1.96. Now, next, let's find out what will change if I slightly alter the level of significance. So let's consider a 1% level of significance, which is alpha being equal to 0.01. So the left and right extremes must add up to give us 0.01. So since they are of equal size, we have 0.005 as the area of one critical region along the right extreme and 0.005 as one critical region along the left extreme. So the confidence interval is in the middle, the critical values form the border, and the critical regions are on the extremes. So now to find the critical value, we'll once again use the normal distribution chart. So the area to the right of the critical value is 0.005. Therefore, the area between the origin and the critical value will be 0.5 minus 0.005, which is at 0.495. The nearest value of Z of the critical value, which has an area of 0.495, is evident from the chart, and that is at 2.58. So therefore, we conclude that for a two-tailed test at 0.01 level of significance, the critical values are at 2.58 and minus 2.58. Now, what happens if we make another change? What happens if we go for a one-tailed test at 0.05? So this one-tailed test could be a left-tailed test or a right-tailed test. The right tail test, the critical region is along the right extreme, and for the left tail test, we have the left extreme. And the area of the critical region is 0.05 in this case. So we find out the exact value of the critical value using the same technique. So the area to the right is 0.05. So the area between origin and the critical value is at 0.45. So referring to the chart, we see that it is 1.65. So we conclude that at 0.05 level of significance for a one-tail test, the critical values are plus 1.65 for a right tail test and minus 1.65 for a left tail test. The changes in the signs is obvious from the images that we see here. So what we'll do next is we'll focus on a different level of significance at 0.01. So the left extreme critical region has an area of 0.01. The right extreme critical region will have an area of 0.01 again. So that's what we have. So to find the critical value, we'll use the chart again. The area to the right is 0.01. Therefore, the area between the origin and the critical value will be at 0.4900. So that, according to the chart, is the 2.33. The closest value is the 2.33. Therefore, we conclude that at 0.01 level of significance, the critical value for a one-tailed test is plus 2.33 for a right-tailed test and minus 2.33 for a left-tailed test. So having identified how these critical values are being solved for, we'll go to specific problems on hypothesis testing. The first problem is about a sample of 100 students taken from a large population. The average height of the samples is at 159 centimeters. But the claim is that can it be reasonably regarded that the population, the mean height is 164 and the SG is 10 centimeters at 5% level of significance. So we'll note down all that we need. The sample average is at X bar at 159. The population average is the mu at 164. The size is 100, that's greater than 30, and therefore we have a large sample. The population standard deviation is at 10, and the level of significance is at 5% or 0.05. So the claim that we identified in the question is that the average height is 164 of the population. So mu is equal to 164 will be the claim that is being tested, and we see that it involves an equal to symbol, and therefore that is the null hypothesis. So the corresponding opposite statement, mu not equal to 164, will be the alternate hypothesis, and therefore we have two-tailed test. So we have completed 4 steps in the procedure. We have identified the sample size, we have defined the null hypothesis, we have defined the alternate hypothesis, and we have also found out what kind of test we are solving. So based on this, we have our test statistic defined as Z is equal to X bar minus mu divided by sigma upon root n, where X bar is the sample's average, mu is the population's average, sigma is the population standard deviation, and n is the sample size. Substituting the numbers into the formulae, we see that the calculated value is at -5. And we know that for a two-tailed test at 5% level of significance, the critical values are at 1.96 and -1.96. Now we see that our calculated value falls in the critical region. So it is in the shaded region, therefore it needs to be rejected. Or equivalently, you can also understand this by finding the absolute value. So Z-cal falls in the critical region, therefore H naught must be rejected. Or equivalently, when you find out the absolute value symbol, we see that the Z-cal is greater than Z-tab. This 5 is greater than 1.96. And as a result, also, we conclude that H naught must be rejected. So since H naught is rejected, there is no sufficient evidence to support the claim that the average of the population is at 164. The next example is about the mean breaking strength of cables supplied by a manufacturer. The manufacturer claims that the breaking strength of the cable has increased. In order to test this claim, a sample of 50 cables is tested and is found that the mean breaking strength is 100,650. The question is, can we support the claim at 1% level of significance? So as usual, we'll find out the sample size, which is 50 and a large sample. The population average, which is known from the manufacturer, is that it is 1600. The population SD is at 100. The sample average has been found to be 1650, and we have alpha at 0.01. So since the claim states that the average breaking strength has increased, which means the alternate hypothesis will be reframed as mu is greater than 1600. So mu is greater than 1600. So its exact opposite is mu is less than or equal to 1600. So in this case, we see that the alternate hypothesis has a statement that is greater than 1600. And because it's a greater than symbol, the test that we are performing is a one-tailed test and a right-tailed test. So the test that we have here is a right-tailed test. So the test statistic does not change. It is still at Z because we are comparing averages for a large sample. We find out the value of the test statistic and it happens to be 3.54. Now, we have already seen that for a one-tailed test at 1% level of significance, the critical value is at 2.33. Comparing this with the calculated value, we see that our test statistic falls in the critical region. Therefore, H naught must be rejected. Or equivalently, when you compare the absolute values, we see that the calculated value is greater than the tablet value, which will also mean that H naught is rejected. So therefore, we conclude that there is no sufficient evidence to state that the average breaking strength has in fact increased. The third problem goes on like this. The average height of a male student in a city is known to be 185 centimeters. A sample of 121 male students from a different city shows an average height of 183 with a population standard deviation of 10 centimeters. Test whether the mean height of the sample is significantly lesser than 185. So once again, the sample size is at 121, a large sample, and the average of the sample is 183. We're comparing this to population SD of 10 and a population average of 185, and we have a level of significance at 0.01. So we say that the mean height of the sample is less than 185. Therefore, HA is X bar is less than 185. So the corresponding null hypothesis will be that X bar is greater than 185. So the alternate hypothesis has the less than symbol and the null hypothesis is a greater than or equal to symbol. Since the less than symbol is in HA, we have a left-tailed test. So we use the same formula again and we find out that the calculated value is minus 2.2. We compare this with 2.33, which is known to be the critical value for a one-tailed test at 1% level of significance. We see that our test statistic falls in the confidence interval and not the critical region. Therefore, H naught is accepted. Or alternately, you can compare the absolute values and see that the absolute value of Z calculated is less than the absolute value of Z tabulated. Therefore, we observe that H naught will be accepted. And there is significant evidence to support the claim that the sample average is in fact less than 185. The last problem that we discuss is like this. The mean and SD of a sample of size 100, the mean and SD of a sample of size 100 are 60 and 4, and another sample of size 200 are 62 and 6. Now we are supposed to test at 1% level of significance whether the from averages, the means of the two populations from which samples have been drawn are equal. So we once again list down the data. N1 is at 100, N2 is at 200, X1 bar is at 60, X2 bar at 62, S1 at 4, the sample standard deviation, and S2 is at 6. So to check the claim that the population's averages are equal, we have mu1 is equal to mu2. Therefore, the corresponding alternate hypothesis will involve mu1 not equal to mu2, and therefore it is a two-tailed test. And hence we have critical region along both extremes of the sample space. The formula is slightly different because we are comparing two sample averages. So zcal is x1 bar minus x2 bar divided by the square root of s1 square by n1 plus the square of s2 by n2. Substituting the numbers, we see that the calculated value is at minus 3.43, and comparing this with the two-tailed test at 1% level critical value combination, we see that for a 1% level of significance and a two-tailed test, the tabulated value is at 2.58. The critical value is at 2.58. So our test statistic falls in the critical region and therefore must be rejected. Or equivalently, if you compare the absolute values, we see that Z calculated has a greater absolute value in when compared with Z tabulated. So the conclusion that we make is that the statistic falls in the critical region and therefore the null hypothesis must be rejected. So there is no sufficient evidence to support the claim that the averages of the population from which the samples have been drawn are equal. So the claim is in fact rejected.